It's not coming in the final, nobody show up. That's the problem I have with this problem. The mentality should be you're not here for the final, for the grade. You're here to learn, right? So given this, I think you are suggesting to me, not you guys, that since you have more time to study for the final, I should make my final tough. Right? I mean, that's a fair game, right? Okay, so anyway, I will still continue the discussion that we started on Monday. So basically, I promised you to cover two things, which I started on one thing, which is the data storage inside this kernel. I will finish that discussion using about 20-30 minutes of today's lecture. Then I will branch into the second topic I promised you to talk about, which is NoSQL systems. Okay? To give you a quick overview of that, I'll wait for the projector to. Okay. Today will also be the last lecture of the semester, right? So we will not have additional lectures next week, so that you can focus on two things. One is getting your phase 3 done, and as well as doing your revision for the final test. Okay. All right, so let's continue from here. So last lecture I talked about how disk works, hard drive works, and explain to you why reading data from disk is expensive, because you have to move the arm head as well and wait for that rotation to happen in order to be able to read data from disk surface. I also briefly talk about the difference between magnetic hard drive disk with solid state drive disk. Both are durable, meaning they both offer persistent storage. But solid state drive is much more efficient in terms of reading data and writing data from it. However, solid state drive is super expensive in terms of doing random writes to a block on solid state drive, because it has to go through the expensive eraser block operation, as I explained. Okay, so that's just a quick recap of what we said last time. Now we're going to move on to the next component in the kernel is called buffer. The fundamental reason we need to use a buffer is really because of this. Because of this memory hierarchy that exists in a computer, right? Hard drive, solid state drive, they are durable and they offer large storage space in a relatively cheap price, $1 per byte, compared to memory. However, your CPU cannot operate over data from this durable storage media directly. In fact, CPU can only operate over data stored in cache. So this brings up this interesting challenge of data transfer, meaning moving data from hard drive and solid state drive to memory, then move those data from memory to cache. Okay? If you do not do anything special, you end up moving data between these different storage medias all the time. So you want to minimize data transfers, because data transfer is expensive, okay? As we argued. So how do we minimize the amount of data transfer you have to do? For that purpose, people introduced this thing called buffer. So buffer is really, before I talk about buffer, right, let's look at why don't we store everything in main memory? What's wrong with that? What's wrong with storing everything in main memory? Well, first of all, it costs too much. Main memory price, $1 per byte, is still much more expensive than $1 per byte for disk, either solid state drive or hard drive. Okay. Secondly, main memory is volatile, meaning if you lose power or system crash, whatever you store in main memory will be gone. So this is the approach of buying more memory. This is super expensive, but in fact, this is an approach adopted by a lot of companies, like Google, Facebook, Microsoft, in their cloud computing platform. Sometimes they offer you this approach, okay, which I'm going to talk a little bit when I branch into the NoSQL discussion later today. Okay? But this is an expensive approach, and probably not scalable. You can probably afford to have hundreds of thousands of machines, each has big memory space, but you cannot afford to scale this to beyond that, okay? Because memory is still super expensive, okay? So alternative choice is to do this, but then this brings up this random access versus sequential access challenge, which I talked about, right? For random access, you have to move the arm, wait for the rotation. For sequential access, you move the arm once, then you just wait for the rotation to continuously rotate data you want to read from the to place those data under the heart of your arm, under the head of your arm. Okay, so this is a closer look at what happened in a hard drive, magnetic disk. This is the platter surface I talked about. These are magnetic surface. Okay, and these are the sectors I talked about. All the sectors with the same radius to the center of the disk form what we call a track. So this is the head of the arm that's capable of converting data from magnetic field to data represented by electrons in main memory. Okay? So that's where the conversion happens. So the way it works is the spindle gonna spin in one direction all the time using that RPM parameter. Right, that dictates over how fast you can rotate. So this spindle is rotating all the time. Taken together with the spindle is all the platters. They're gonna rotate with the spindle all the time. Okay, and then this arm just moves in and out. That's how you kind of align the head of the arm with any particular sector of data you are trying to read. Of course, in a database system, you don't read data in the unit of sector, you read data in the unit of page. A page is nothing else but a collection of consecutive sectors. For example, if I tell you the page size is 4 kilobytes, and each sector is 512 bytes, then we are talking about a page of 8 consecutive sectors. Okay? So that's kind of the basic idea behind this. So I'm going to skip a lot of these details. I'm going to show you just one thing. So this is what happened to a sequential rate. This x-axis is the time. Y-axis is the offset. The offset from the starting location of the first byte you have read. For sequential access, obviously this offset value will be a linear curve like this. So what happened is, you basically imagine that you move your arm to a particular track. Then what you try to read will be pages after pages after pages from that track. Meaning that you no longer need to move the arm in and out anymore. You just wait for the rotation to happen automatically. Okay? Of course, you may wonder what happened if I reach the end of that track. I have finished reading all the pages from that track. At that point, you do need to move your arm again to the next track, then to the next track, then to the next track. But this is much better than moving your arm, wait for the rotation, read one page, then move your arm again and read another page. Okay? Which is much better. So this is essentially the pattern it looks like from a sequential workload. Now if I add a random workload, this is how a random workload looks like. The offset value is all over the place. Do you see the difference of the two? Sequential workload and random workload. in practice, there is typically an order of magnitude difference in terms of efficiency. Meaning that if you do sequential access of 100 pages versus random access of 100 pages, the latter will cost 10 times more time to finish.
So obviously random access is pretty bad, but
yep.
How would you avoid random access?
How would you avoid random access? That's essentially what we're going to talk about next. Okay? So we're going to use something called buffer to minimize the number of random access you're going to perform from disk. So the basic idea is the following, is that, okay, I'll give you a metaphor or analogy to this, right? So every morning, before you step outside your house, you find the jacket you want to wear today. Like every morning, I find this jacket I want to wear today. And I don't know about the setup in your apartment, in your house, but in my house, I have a closet in my master bedroom where I store most of my clothes at. Okay? That's kind of like a disk. Durable, large, occasionally you go there and fetch the clothes you want to wear. That's your disk, hard drive. And typically in my house, and typically this is true for most apartment and house as well, right next to the front door of your house or apartment, there's another small closet, much smaller than the one in the master bedroom, that allow you to hang some clothes over. Do you see what I'm saying? That's your buffer. You cache the clothes or the jacket you wear on a daily basis in that second closet close to your front gate. Why? Because it's convenient. Whenever you need it, you just go and fetch it and get it, ready to go. You don't have to pay a visit to third floor of your house with that master bedroom closet where all the data are located at. So that's the relationship between disk and buffer. Okay? Using this simple analogy, you can kind of understand what's going on here, right? This brings up an interesting question, which is what clothes or what pages you want to place into that buffer, into that closet close to your front gate. Seems like an easy choice, right? Well, whatever you're going to wear every day, you're going to place over there. But the thing is, what you wear on a daily basis may change over time. I don't know yet a single person who's going to wear the same jacket for the next 3 months. If you know this person, let me know. But actually, take back what I said. When I was in grad school, we have students like that, right? Until one day somebody told him, dude, it's time to change for another jacket. And he was like, what's wrong with it? Okay? But typically, that doesn't happen, right? You are requesting different pages of data. And what's the problem? The problem is your closet space is limited. You cannot afford to cache all these closets from your master bedroom closet to that smaller closet right next to your front gate. So you have to make a decision what you bring to the buffer and what pages you want to cache over there. Okay? So this is called the buffer management. And an important topic under this is buffer replacement algorithm. I won't go into the details, but I want to point out to you the basic structure of how we implement buffer. So this is, each of the frame here represent a page in main memory. And a darker color frame indicates that that frame is used to cache a particular page from disk. So the way it works is that so you have disk, this is your hard drive and solid state drive. Okay? Durable storage. And then this is your RAM, your memory. And inside your RAM, you allocate some space for your buffer. So suppose this is your buffer. Obviously, you cannot use all the available memory space for database buffer because you have to reserve some space for operating system, for other applications running on that machine, right? So you use some of the space from your memory as the buffer. and the buffer is partitioned into pages or frames. So what's going to happen is on disk somewhere you're going to have some pages. Page 1, page 2, page 3, page 4, and so on and so forth. Right? Somewhere on disk you have those pages. This is a page. Now, then there's application, right? By requesting different pages. But application in the context of database, typically this refers to transactions. Different transactions asking for different pages. Like read object of read page A, write page B, and things like that. Okay? So far so good? So what happens is you're gonna pin a page to the buffer. So why people call this pin a page to a buffer? Okay? The reason is let me take so suppose this is a page. This is literally a page. Okay? This is your buffer. This is buffer. Why we call this pin a page? Because if you just bring the page to the buffer, once you are done with it, what happens? Page is gone. What if you keep requesting this same page? Well, you want to pin the page, right? Now, imagine this is like a pin. Now you request this page. After you're done with it, if your prediction is somebody else, another transaction, or yourself going to request the same page again, instead of letting the page exit the buffer, you pin it over there. That's why we call pin the page. You understand this? Okay? And when you have pinned the page, sometime later you have to unpin the page. Like you remove the pin, page is gone. That's called unpin the page. Okay? So that's the basic idea. The essential challenge then is when do you pin a page and when do you unpin a page? And in fact, a page can be pinned multiple times by different transactions. The first guy say, okay, this page is important. I want to pin the page in the buffer. But then another transaction said, oh, this page is important for my business logic as well. I'm going to pin the page again. So you have two pins on the same page. What's the implication of that? The implication is if the first transaction later come back unpin the page still stays because it's still pinned by another transaction. You follow this model? So a page is only to be removed when it is unpinned by everyone who had pinned the page in the first place. And in order to do that, we need to maintain a counter that's called pin count. So pin count initially is 0 and goes up to some value, then decrement back to 0 when all the transactions using that page are done. And you can only kick a page out of buffer when pin count is back to 0. Okay, so that's number one. Number two, what if I have multiple pages with pin count equal to 0? What I do, which page to replace? First of all, if you have available frames, you don't have to worry about page replacement, right? In this case, I only have 3 frames occupied. Most of my frames are still available. So I can use those frames for to pin other pages. But at some point, you will end up with a full buffer where everybody is pinned. There's no space. And suppose now another transaction comes in and says, I want another page. I want to pin another page, but we don't have space. What do? In this case, you're going to find a frame with pin count equal to 0 and replace that. But what if you have more than one frame with pin count equal to 0? What do? That's challenge number one. Challenge number two. when I pin, suppose somebody say pin page 2. So what's going to happen is I'm going to load this page to some frame. So let's say I load it here. Now this frame will be a copy of page 2 from disk. So far so good? Okay. Now let's assume this transaction later says write page 2. So make some update. So this copy of page 2 now becomes a different image. Like this part becomes black. So it's different from, it's no longer equal to this. This copy on disk. You follow this? So far so good? This brings up a lot of challenges. Remember, transactions need this assay property. In particular, it needs atomicity and durability. Atomicity and durability. If system crash, this whole thing is gone, including this page in the buffer. Okay? You follow what I'm saying? And let's say that transaction has commit before this. And system now crash. What's the problem with this? And someone tell me what's wrong with this setup. If this happens, what's wrong with it?
Don't you lose what you committed?
Yeah, you lose what you have committed. Durability is not satisfied. You follow this? Which means, at some point, this is what we call a dirty page. At some point, this dirty page must be pushed back to this so that this page becomes the same as that. You follow this? That's challenge number 1. Challenge number 2. Okay? Let's assume a different scenario. Let's assume that system crashed, but you haven't committed yet. Transaction has not committed yet. To fix the durability challenge, we said, okay, you push this back to disk. But that creates another dilemma for us, which is, if you haven't committed yet and system crash, and yet you have pushed this back to disk, what happens? What happens? It violates the atomicity requirement. Atomicity says if the transaction has not committed yet, system crashing, you are forced to roll back, then the entire system should like this transaction had never happened in the first place. But that's no longer the case, right? Because this change is already reflected. So you need to somehow magically get rid of this and restore this page to its original content. But how? How do you do that? Once it's overwritten, the original image is gone. How do you somehow remember what the original image is? So that's where buffer management and transaction management intersect. So buffer management and transaction management has to go hand in hand to address these issues. Obviously, I don't have time to go into the detail of that, but that's a really fascinating topic and a really deep topic to discuss as well. We don't have time to go over that. Okay, that being said, I do want to talk about buffer replacement a little bit. Let's say my buffer is completely occupied. At some point. Now, somebody said pin page 102. And you search through your buffer, and you figure out that page 102 is not there. It's not there. What do? Well, you need to find a frame to replace so that you can find this page 102 from disk and bring that to the buffer. And the question is which one you kick out. Like I said, you can only kick out those with pin count equal to 0. That I have already explained. Follow that? So let's say the pin count is 1, 2, 3, 2, 1, 1, 0. something like that. So these two are the candidates, let's say. Only these two with pin count to 0. Then you face a dilemma, or challenge, which one to replace. For that, people use different replacement policy. One commonly used policy is called least recently used. You can also use most recently used. But none of this policy is perfect. Let me give you a really simple illustration of this. Why none of this policy works well. Okay? Let me give you a simple setup. Let's say my buffer frame is 4 pages, and on disk I have 5 pages. You see that? Okay, so my buffer is 4 pages. 1, 2, 3, 4. Initially empty. My disk has 4 pages. And I call that page 1, page 2, page 3, and page 4. And let's say I have, yeah, go ahead.
You said 5 or 4?
5. Let's say I have an application or multiple transactions asking for these pages. And let's say they are doing read-only access. Read-only access means they will pin the page, meaning pin count will be incremented by 1. Then once they have read the content of the page, they're done with the page. They will decrement the pin count back to 0. So for each of this page brought to the buffer, this is a really simple case. The pin count will go to 1 for a short period of time, then be decremented back to 0 immediately after that. So my request sequence will be, let's say P1, P2, P3, P4. I request them sequentially. By the way, requesting them sequentially does not necessarily mean you will end up with sequential access on disk. It really depends on how these pages are arranged on disk. Okay? So what happened is you got P1 here, P2, P3, so far easy. And pin count is basically 0. Because you have available frames. You just use an available frame for a given page. You're done. Now I ask for P5. Okay, which one to replace? If I'm using least recently used policy, which one I should be replacing? P1. P1, right? Because P1 is the least recently used. So I got P1. The intuition is the following, right? You're betting on if some page in the buffer hasn't been accessed for a long time, it will not be accessed in the future, at least in the near future. So you should kick that out of the buffer. But imagine if you think about this as a game. I'm the adversary. So I observe what you do and design my move based on what you do. If you choose to replace P1, I will request P1. Okay, what happens now? If you're using RRU, you will replace, no, P1 is kicked out from the buffer, right? So you have to go to the disk and fetch P1. Now which one to replace? Using RRU, which one is to be replaced? P2. P2. Now I observe what you do. I say I'm going to ask for P2. What happens? Now you have to go fetch P2, and you replace P3. And I'm going to request P3. Now I don't have to continue, right? You see exactly what happened, right? You are doing the worst possible move from your perspective. You are replacing the page that somebody gonna ask for immediately after you have replaced that from the buffer. So that's the problem with our LRU. You may say, okay, in this case, maybe I should use a different policy. If you know the future, and you know this is what's gonna happen, let me restore to this particular state. If you know that's what's going to happen when P5 is here, which one you should be replacing? Which one you should be replacing? Huh? If you know this is what's going to happen next.
P4?
Yes, obviously. Why? Because this is the optimal strategy. Now, P1, you no longer need to pay a visit to the disk. You no longer need to pay a visit to the disk to get these guys. So this request will be served immediately without a revisit to the disk. However, think about this as a game, right? I'm the adversary. If I know that's what you're gonna do, I will change my request sequence. If I know that's what you're gonna do, you're gonna replace P4, right? So I'm gonna request P4. I'm gonna request this way. So this is essentially when you replace P4, you are using a policy called MRU, most recently used. I mean, there's some justification to that as well, which is if you have just looked at a data item, the chance you're going to come back and look for the same data item is low. You have just looked at it. Why you want to look at it again? So that's the intuition behind the design of MRU. But I'm hoping that using the simple example, I can convince you that neither IRU nor LRU is a perfect strategy for what's going on. Right? So what is the standard? Believe it or not, in most commercial database engines, they're using one of these really simple, naive algorithms, RRU or MRU. What is the state of the art? Like, for example, in our research, what we're doing is we're building a machine learning model to predict what's going to happen next. And using that machine learning model, we can make better cache replacement decisions. That's one approach. The other way of thinking about this is why you have to stick with RRU all the time. If I have a collection of cache replacement algorithms, RRU, MRU, I still have a decision to make, which is for this period of time, RRU works better. For the next period of time, MRU works better. So I want to design a machine learning algorithm to do that switch automatically. Does that make sense? That's another way of looking at this problem. Yeah.
With MRU though, if you do like reads, 2 reads, each one on a different page, let's say you write to one of the pages, wouldn't that kind of make it really inefficient?
When you write to one of the pages, that's considered another access to that page.
Yeah, but I'm saying if you, let's say you're full, and then you had one read, so you pull the page.
Yeah.
And you had a second read, so you pull, so you would actually overwrite the page you just pulled.
Not necessary. If I have another available frame, why I want to replace that, right? Your buffer doesn't just have just one page, right?
No, but if you have, let's say you have a full buffer.
Yeah, full buffer.
And then say
yeah, I understand what you're saying. That's exactly what happened here. Yeah, but MRU, you're betting on if a page has just been accessed, it won't be accessed in the future, right? What you're saying is if some transaction is reading a page and then writes a page, okay, I think you missed the point I was just saying, the pin count. This cannot replace this because from transaction 1 point of view, I will not decrement the pin count back to 0. I'm not done using it. Okay. You follow what I'm saying? The pin count on that page A will not be 0. So this B will not be able to replace that because from transaction 1's point of view, transaction 1 knows what he wants to do. So transaction 1 will not decrement the pin count until I'm fully done with the page. So you cannot even replace that page. Okay? So that's the purpose of pin count. Okay? So that's buffer management. As you know, next I'm going to talk a little bit on. You have these tables, right? Student table, course table. All of these tables, how are they organized on disk? Okay. Typically they're organized on disk using something called heap file. A heap file structure. A heap file structure is as follows. So a table is nothing else but a collection of pages. Each page is nothing else but a collection of records. So 10, for example, 10 student records go to a page. Why? Because maybe a page has 4 kilobytes and each student record is 400 bytes. So you can fit about 10 student records into a page, right? But I have millions of student records. What do I do? Well, you organize them into multiple pages. But somehow these pages need to be logically linked together so that you know they are from the same table. That logical organization is called key file. And the basic idea is as follows. You have a header page, then you have linked lists of these pages. And you do differentiate two types of pages. Those pages with no free space left, and those pages with free space left. Why do you want to make that distinction? Because later on, if I try to insert a new record, you should go to that second linked list for those pages with space still left. Because those pages with no free space left, you know you're not going to be able to accommodate any new record to that. So this is one way of organizing pages on disk. Really simple, works well. However, it has its shortcomings. For example, if I ask for students with GPA value between 3 and 3.4, with this organization of your data records, what can you do for answering that query? Student between 3.0 and 3.4 GPA. Yeah. Yeah, excellent. You have to scan through all the pages because there's no semantic organization at all on how those records are located in your page, in your data file. So you have to linearly scan through all the pages. You see that? Which is gonna be super expensive. And this is actually a good time to introduce another concept that we don't have time to cover, but super useful in practice, called index. Index is nothing else but, you can think about that as a data structure built on top of this data file with your records. Somehow this index tells you magically where records are with respect to some semantic meaning attached to those records. For example, if you have an index on GPA, then it can somehow quickly tell you where are those records with GPA between 3 and 3.4. You may wonder how that's done, right? All of you know binary tree, right? Do you know binary tree? Or you don't know binary tree? You do, right? Or you don't? You don't know binary tree?
Oh, binary.
Binary tree. So let me give you an example how binary tree works. Let's say I have a set of integers. And the set looks like this. Okay? Now I ask you, give me all the okay? How would you solve this problem? Can someone tell me how would you solve this problem? How would you solve this problem? Go ahead.
Sort, and then return the range 7 through 15.
Okay? Is this the optimal solution for this?
No.
What's the sorting cost? Can you tell me?
N log n. Yeah.
N log n, right? And what about the second step? Return the range from here. Once you have sorted, what's the cost of doing that second step?
Potentially n.
Potentially n. Then what's the purpose of sorting? It's log n, right? The second step is log n. Once you sort them, let's say you sort them. You got something like this. How do you find this range? Well, you do a binary search. You start from the middle, 7 less than this. Yes, then you find the middle of this, then you, right? And each time you cut your range by half, henceforth finding the range, the starting point of the range is just log n. But this is not the good solution for this problem. If I ask this question only once, why you are willing to pay n log n cost to do this? If you just do a linear scan, you can answer this in n time. Right? I just check one by one. If the element is in the range, output, otherwise escape. Why I want to do sorting? For what? If you answer this question only once, you follow what I'm saying?
Mm-hmm.
Sorting actually make it more expensive. There's no point of doing sorting. This is not a good approach. Okay, not a good approach. But now imagine you're not doing this only once. Then I will ask you. Now I ask you this question all the time. If you stick with this linear scan approach, you are paying order n cost for each of this. Do you follow me? So your total cost become m times n. M is the number of queries, n is each time you do a linear scan. So far so good? Do you follow what I'm saying? What about that sorting approach? The sorting approach will be you pay that sorting only once, because once it's sorted, it stays sorted. And then for each of the query, how much time you pay? Now, these two values, which is bigger? Which is bigger? Which is smaller?
Doesn't it depend on M?
Depend on M. Yeah, excellent. Depend on M. Do you follow that? Now there's a point. If M is big, there's a point of paying the sorting cost once for all. You wonder, okay, still, how big an M can make this meaningful to do this? If you talk about Google, if n is number of items they have, n is like a ridiculous number. Okay? This brings up another topic we haven't talked about, which is called external sorting. The idea is you don't sort items. You don't sort based on item. You sort by page. So this n, small n, is no longer the number of records you have, but the number of pages you have. Number of pages is way smaller than number of records you have. Typically, it's 2 order or even 3 orders smaller than number of records you have. Why? Because, go back to the earlier example, right? If each record is 40 bytes and you have 4 kilobytes page, how many records can fit in a page? 100 records per page. And that's 2 order of magnitude smaller, number of pages versus number of records. In that case, n is a very small value. But m, imagine how many users are querying Google all the time. M is a huge number. Then this pay off. Okay? Now, what is the binary tree? What's the connection of all this discussion to binary tree? Well, if you have stored your data set like that, you can leave it like this and do this binary search all the time. Or alternatively, say I maintain a tree structure on top of it, so I can do my binary search much more efficiently, rather than doing this binary range search all the time. So what I do is, write down my stuff, then I maintain a tree-like structure on top of it. So eventually they meet up on the top. So the way you read it is this is greater or equal than, this is less than the value at the node of that tree. Now you can descend down this tree accordingly based on the value you're looking for. That's called binary. And what about index for database? If you understand what I said so far, index is one particular index is called B tree. And this B does not stand for binary. It does not stand for binary. It actually stands for a block. Block level tree. Block. Blocking. Basic idea is similar to binary tree, but instead of storing a single value at each node, you store a page of values at each node. And this tree, the fan out, this is called the fan out. How many children node you have? It's no longer 2, is whatever number of values you can index per page. So the tree becomes like this. And this will make your query processing much more efficient. And then, of course, once you have this indexing structure on top of these pages, you introduce all sorts of challenges. How do you work with transactions? What about ACID? Because if you have index on top of data files, whenever you update your data file, you have to update the index pages accordingly. But the update to those index pages need to satisfy the ACID property as well. Right? That becomes tricky, super tricky to deal with. All right, so all this discussion I'm going to skip. Okay. Now, so that's page and index. What about record within a page? Well, then here we talk about. Remember, at the beginning of the semester, I told you there's this, difference between we talk about the difference between these two, right? Char 20 and varchar 20. Char 20 means that I give you a character array of 20 characters, meaning 20 bytes. Varchar 20 means that I give you a character array of up to 20 characters, meaning up to 20 bytes. The actual length of an element in that array could be anywhere from 0 to 20 bytes. But if you're using char 20, then any element going into that array must be of 20 bytes. That's the difference of the two. But fundamentally, the difference is fixed length versus variable length. And this leads to fixed length, this leads to variable length. The record length. Okay? Within a given record, I may have multiple attributes or fields. F1, F2, F3, F4, in this case. I have 4 attributes. And they have different length. If each one of them is of fixed length, meaning like data type such as integer, double, or like this, all of these guys are of fixed length. Meaning no matter what the actual value are, they're going to occupy the same number of bytes on disk. You could be having value of 5, I could be having value of 10 as integer. But once we represent that on disk, it's 4 bytes. Integer is 4 bytes. Period. Right? No matter what the values are, we all end up with the same length. If each attribute of your schema is like that, then you end up with fixed length record. All you need to do is to figure out where the boundary is between 2 attributes. Why? Because in order to do this, to support the projection operation, if I do projection, imagine this is what you do. You need to figure out where is that name attribute in order to project it out. You follow what I'm saying? For example, let's say name is the 3rd attribute. This is name. Then I need to know the boundary of this as well as this. So I can pass out the correct number of bytes and return that as the name value for the current student record. For fixed length record, this is easy. Why? But all you need to know is the base address. Then you just add the corresponding length of each attribute to figure out the base address for the name attribute. Right? You follow this? All you need to know is the length of each attribute. Then you can figure out how to calculate this offset properly. And since for each record, this offset is a fixed value, because we're talking about fixed length record, this doesn't create too much overhead for the underlying database. I only need to store these values once for the schema. Once for the schema, for the entire schema. And there are different, what about variable lengths? Variable lengths become really tricky to deal with. There are really 2 ways to work with variable lengths. One is you use a special delimiter of some sort, like a $sign. Suppose $sign is never used in database record. which is obviously not true, but imagine there is a special delimiter like this. You put this special delimiter in between any two attributes, then you can do the parsing of two consecutive values for any given record. You just keep going until you find a delimiter that tells you, okay, that's the end of the current value and the start of the next value for two consecutive attributes in a record. You follow this? Another approach is to say, at the beginning of the record, I'm going to allocate a metadata array like this. Remember the offset address, like pointers, to the beginning address of each value. That's another way of dealing with this. Both approach, if you think about it, introduce way more overhead than fixed length record. Why? Fixed length record, the length of each attribute is fixed for all records for a given schema. But for variable length, each record, the length of each attribute for each record may be different. So you have to introduce these guys for every single record. Obviously, that's way more overhead than fixed length. But on the other hand, it does offer you more flexibility. If a name is only 3 bytes, then you use only 3 bytes instead of using 20 bytes all the time.
So the varchar 20, that 20 is the limit on how big the variable could be, right? Or how
for
big
that
the
attribute, for that attribute.
So what
attribute. Not for the entire record, only for that attribute.
For the attribute.
Yes. Yeah.
So then why don't you just store up to 20, just make it fixed length?
You can, but what if my name is only 3 bytes? You're wasting 17 bytes of space. Right? And in reality, the longest length of possible name is not 20 bytes. I can tell you that. People have 100 bytes of name. That's not unusual. And are you telling the database, oh, because that's one person, everybody's name value has to use 100 bytes? Okay. So that's variable length and fixed length record. Now that's at a single record level. Now imagine you want to take these records and store into pages. Again, you have two challenges. One is fixed length record. You have a bunch of records you want to store in a page versus variable length record. How do you store them in a page? And I don't have time to go over that, so I will skip this part. Okay? So you can look at this yourself. Okay? So inside a database, the one last thing I want to tell you is inside a database engine, there's something called system catalog. That system catalog will store all this information I just talked about, like variable length, fixed length, how I organize this. And this information are stored as tables themselves. Henceforth, when I go to a database, you know, the reason, oh, it's not showing this, okay. Why it's not showing?
It's showing.
Nice showing, okay, cool. You know, the reason that when I type show tables, the database can actually show this list of tables. And also when I type describe course, it shows this information is because this information is stored somewhere. And how do you store this information? While you are in a database, the best way to store the information is use another table. So all of this information, schema information, and length information are stored just as tables. Now, another thing I want to demonstrate to you is the power of index. In particular, I'm going to show you two tables, test 1 this is, the structure of test 1. And test 1 does have an index B tree index on the rating attribute. Okay? And let me describe test 1. So that's a schema of test 1. I'm going to describe test 2 as well. Same schema. So they have same schema. Two really simple tables, a primary key, ID, the name of a person or whatever, or object, then a rating value between 1 and 100. And each table has about 500,000 records, 500,000 records. Uniform distributed over the rating space, meaning there are equal number of rating record with rating equal to 1, equal to 2, all the way to 100. So that's good? Yeah? Okay. The only difference between the two tables is that on test 2 table, there's no B tree on the rating attribute. That's the only difference of the two. Now I'm going to run this query. I'm going to run this on test 2 first. So as I said, the rating value between 1 and 100 and uniform distributed, all records have uniform distribution on the rating attribute. So I'm selecting about 5% of records. With 500,000, 5% is about 250,000, but 25,000 records. Let's look at what we got. It's called ratings, I guess. Okay. So this query will be is running. So take about 9.45 seconds to return me that 250,000 records. That's good? I'm going to run the same query on test 1. No trick. Okay? See the difference in running time? You see the difference in running time? Okay. Now I'm going to run this one more time. Test 1. See the difference in running time? Can you explain to me why we go from 2.59 to 0.22 seconds using the knowledge we learned today? Huh?
Buffer.
Yes. Those pages from index initially are on disk. So the first time you run it, you are paying a lot of random I/O to bring the page. The root page, then you do binary search, next page, so on and so forth. Second time you visit, buffer. What if you run that? What happened now? Can you guess? On test 1, what's going to happen? Oh, not test 1, test 2. You know what will happen here? It doesn't help. It helped a little bit, but it doesn't help that much. Why? Why buffer is not kicking in here? Because there are too many pages. The buffer size is limited. We're doing replacement. Okay? All right, so I hope this simple experiment helped you understand what's going on in Google, Facebook, Microsoft. It's all about tuning this to the hell out of it. We're talking about just 500,000 records. 500,000 records to Facebook, to Google is really nothing. Like nothing. Okay?
Can you run it again, test 2? Sorry. Is it because
I just run it.
does indexing help buffering?
No, test 2 doesn't have index.
Okay. So if you run it again,
I run it again.
Without
I explain
running,
why it doesn't help that much is because test 2 without index you're doing a linear scan over a lot of pages. But your buffer size is small, you only can cache that many pages. So it helps a little bit, but it doesn't help that much. unless you increase your buffer to a really, really big size. Okay. Now let me move on to the next topic I want to spend a little bit of time on. I have about 20 minutes left. All right, NoSQL systems. So people, you guys might have used some of these systems. NoSQL systems, it sounds like, no, you don't want to use SQL, that's why it's called NoSQL, but it's actually not. It's called not only SQL. Not only SQL. Okay? And it is for working with unstructured data instead of working with structured data using relational data systems. So NoSQL system originates from this simple request that the size of my data is way bigger than the disk and memory space on a single machine. Single machine, I have a really powerful machine in my lab. We have about 40 terabytes of data, 45 terabytes of hard drive, and 2 terabytes of SSD, 256 gigabytes of RAM, and CPU, server class CPU, 4 of them, each has about 64 cores. Like a powerful machine, right? Sounds like. But the data we are dealing with has exceeded the capacity of that machine in our research. Okay? We are crawling Twitter data all the time. I can show you briefly that system. Yeah? Hope it's running. So we've been crawling Twitter data all the time. This is just to show you, this is all the tweets from this location from this period of time. So if you tweet, you will be captured by our system. And then we can do things like, what are the topics people are talking about, what are the word clouds, things are, people are interested in. You drag on the map, that will change the query, right? You are doing a new range query. And this will be updated in real time. And we can even look at, for example, this person. I can even figure out the trajectory of that person, where you have been. Okay? So you told me, Feifei, I was working on my product in spring break. I went, what's your Twitter handle? Be careful with what you told me. Okay? And this goes back to, there's a time range, right? I can change this. And this goes back to about 5 years. And I can go to, for example, if you think you can escape by check, like you were in Tokyo, for example. Let's see whether I can get to Tokyo. Anyways, there's something wrong with the spatial search. Basically, you can narrow down to any location on the map. Okay? So how do we build a system like this? So currently we have about terabytes of data every day. Just to give you an idea how big the data set is, as we speak, we are crawling Twitter data set in real time. And our data set grow about anywhere from 20 to 30 gigabytes per day. And that's how much data ingests into our backend database every day as we speak. And that's how much data we're talking about. Okay? And we are not only dealing with Twitter data set, we are also working with other type of data sets. For example, if you go to the same system again, I'll show you the Twitter data set, right? But there's a job box to select different data source. For example, you can look at the business data set, where we have crawled business entities across the valley, and you can zoom in, and we automatically show you the Google Street Map view of that entity as well. Okay? So how do we do things like this? Okay? How do we do things like this? If you were to use the existing database engine, it's not going to work. So the way we have done it is we take an existing database engine and hack out of it, modify the kernel and to satisfy our needs. And we use a NoSQL system. In particular, we're using a version of MongoDB, and we've been hacking into the MongoDB kernel to change a bunch of things to enable to do the things we have done. Okay? So how do we do that? So you don't want to store data in a single machine. So you want to store data over multiple machines. Like for example, in Facebook, they are using MySQL, by the way. But they're not using a single MySQL server. They are using thousands of MySQL servers over thousands of machines. And if you have 64 gigabytes of RAM on a single server and you have 1,000 servers, then suddenly your RAM capacity becomes 64 terabytes. Why Facebook care about this? Because Facebook just cannot afford to store data on disk all the time. I mean, you ask a simple query, right? How many users gave a rating between 5 and 90 and 95? And you tell Facebook you have to wait 10 seconds to get the answer. You probably will be fired right away. If I'm a Facebook manager, I'll fire you right away. I don't know about Facebook. I don't care about those whatever crap they're going to show down on me. If you cannot do that in less than a second, you're gone. Your job is done. At least in my team, you're gone. I don't want to work with you. Okay? So how do you do? So that's why you want to make sure your memory size is big enough. So you don't pay visit to disk all the time, which is super expensive, as I demonstrated to you. But then if you cache data in memory, you run into all these problems of consistency problem. Like if you're running transactions, I explained that a little bit, right? What about atomicity? What about durability? What about all those issues? How do you address all of those? And this 64 terabyte memory is not from a single machine, it's from multiple machines. How do you manage data across multiple machines? Who should store what? And where a query should be sent to and get executed? All these challenges need to be addressed. So the first thing you want to understand is called distributed file system. So our computer, I don't know whether you know or not, comes with an operating system as well as a file system. File system. Okay? And a file system on a single node is capable of managing files only from that one machine. Okay? But if you're using this model I'm talking about, you're storing data across multiple machines. So you're managing files across multiple machines. That single file system is not going to work. A single node file system is not going to work. So we want to introduce something called distributed file system. The idea is you have a master node. They have something called trunk servers or client servers. And then you break up a file into multiple trunks, each trunk of some fixed size, like say 64 megabytes. So a 64 terabytes file will be broken into a lot of smaller trunks. Each is 64 megabytes. Then this trunk will go to different physical nodes for storage and processing. And oftentimes, for fault tolerance purposes, a trunk is duplicated at least 2, maybe 3 different physical machines. That's called distributed file system. Okay? Of course, there are many details that I haven't talked about here, which is how do you quickly find out a given trunk? And what about indexing? How do you build an index over this? You may argue, okay, why don't we just do the index you just told me to do? I just build a B-tree index. Well, the problem is these trunks are now located on different physical machines. If you were to build an index, where you store that index? Do you store at the master or what? If you store at the master, then everybody has to go through master before they get their file trunk back. The master becomes a single bottleneck. You follow that? Ideally, you want to do load balancing, right? Million users go to Google server, the 100,000 users go to the first node, 100,000 user requests go to the second node, and so on and so forth. Don't cluster all of them to go to one server, right? You're wearing a Utah Jazz jacket, right? If you go to Utah Jazz playoff game, you don't want to end up go through one single gate, even though the seats are distributed within the stadium. But if everybody needs to go through a single check gate before entering the stadium, that distributed setup is not going to help you. Do they do a single gate? Have you gone to a playoff game yet?
No.
You know, I went to a Denver what?
Nuggets.
Denver, no, not the NBA, not play on the NFL, Denver Broncos. We call it Denver Donkey, anyway. So we went to that game, and it's high security, right? So they have a couple of check gates, but like very few. What end up is like a long queue just to get into the stadium. Once you're in the stadium, it's fine. But the thing is, you're not fully utilizing the throughput within the stadium because of that single bottleneck. So you see the challenge of designing a distributed system, right? So MongoDB is a document store. You know, there are many different NoSQL systems, by the way. Like for graph model, for key value, for document. I'm gonna focus on just MongoDB in the next 5-10 minutes or so. So it's a document-oriented database system is using JSON-style schemas. And it does sharding. Sharding is nothing else but sharding is the process of determining how you break a big file into a distributed file system. Meaning, how do you determine which trunk goes to which physical node? That process is called sharding. Now, JSON data, many of you may be aware of this, is something like this. So if you look at this, it has some structure. It's not like totally unstructured, like a key value store. In a key value setup, you have a key, like a student ID. They have a value. What's inside the value, you don't know. It's just a sequence of bytes. At the runtime, somebody may tell you, you code, oh, the first 2 bytes is the name, the next 10 bytes is this, and so on and so forth. But that may change for the next record. Right? That's key value. JSON is in between of key value and relational schema. Relational schema tell you exactly what each record is going to look like. So JSON is something in between. By looking at this, okay, I know there's the first name, last name, and age. Then there's the address, and the address further has a substructure in it. The nesting JSON structure. But the flexibility of JSON is such that all records from the same table do not have to follow the same JSON structure. The next record, for example, this is the first person record, right? The next person record may not have a phone number, may not have that phone number part at all. That's okay. In structured database, that's not okay. Even if you don't have a phone number value, you have to have that phone number field reserved in place for the next record. Okay? And furthermore, you can change the schema very easily using a JSON approach. Okay, so this is what it talks about, like how JSON model this. And they also have this concept of foreign keys. So for example, I have a user document, I have a content. Document basically is kind of like a table in our relational setup. The way I link user document, user table to the contact table is through the user ID, for example. So they also have this primary key, foreign key kind of concept. You follow this? And they allow you to embed a JSON document into another JSON, so allow you to do nesting. Now, replication and sharding, I'm going to skip this slide. I'm going to go to the sharding discussion. So remember, you have one big file you want to store into, let's say, 10 different nodes. You want to break that big file into smaller chunks. But you need to figure out where to store those chunks at. And there are typically 2 approaches, commonly used approach. This is called sharding. This process is called sharding. There are 2 commonly used approaches for sharding. One is called range-based sharding. The other is called hash-based sharding. What's the difference? Range-based sharding is like you tell the system a particular attribute you want to do the partition over. Let's say location, or age, or income, or rating. Then you define a range-based partition with regard to that attribute. For example, rating from 1 to 10, then rating from 11 to 20, rating from 21 to 30, all the way to 100. That gives you 10 different ranges. Then when you say, okay, all trunks all the file trunks with reading value between 1 and 10 go to first node. All the file trunks with reading value between 11 and 20 goes to second node, so on and so forth. What's the benefit of doing this? Well, if your query is based on the reading value, you can easily figure out where this query should go. And furthermore, if your queries over this rating space is pretty uniformly distributed, meaning that there are roughly same number of queries for rating between 1 and 10 and for rating between 91 and 100, what do you get? You got a balanced load distribution over different nodes in your distributed server. You heard that? What's the downside of this approach? The downside of this approach, if the queries are not done with batch read, you do the range sorting based on reading. Now somebody come in and say, I want to find all view the age between 5 and 20. Then you have to scan all the nodes. You have no choice. You have to do a linear scan of all the physical distributed nodes because you have no knowledge of how data are distributed with respect to that. You follow that? So that brings up the second approach, which is called the hash-based sorting, which is I don't dictate, all the record with value in a particular range go to a physical node. They can go anywhere, but they have to go through a hash function. The hash function take a value as input and a node ID as output, telling you all the record with this value will go to this node. So what's the benefit of this approach is it guarantee almost a balanced load in your server if the queries on different values are uniformly distributed. You're going to distribute them to different nodes. And secondly, it doesn't suffer from this range binding restriction as you will have from this range partition approach. So these are the two typical approach, okay, for distributing data in trunk. There's some additional notes I'm gonna skip. Mongo allow query to be expressed using a similar way, just as we have done for SQL, but the syntax is slightly different. Here I'll give you some comparison, right, of the two. For example, instead of say create table, you will say you create a collection. A collection is like a table. Then you insert one record into that collection with a particular JSON document that will determine, quote unquote, the schema of that collection. Okay. And what about doing some basic retrieval of records? Okay, I'll give you a side-by-side comparison of SQL and the corresponding Mongo syntax. Okay? So on our database server, the system I demonstrated to you, we use 16 nodes, 16. 16 nodes. And the data is distributed across those 16 nodes. And there's a master node with a customized index that we have developed for our application. Okay? With that being said, I think it's time to end this lecture. And reminder, there's no lecture next week. And what you need to do is finish your phase 3. We have 1 day extension, so phase 3 will be due on the 24th, 11:30 in the morning. Just stop editing. You don't have to submit anything. Just stop editing on the server. And then I'll see you on the 26th. Okay? Thanks.
That's why it's 1, 2, 3.